Here's an example where quartz, which is normally clear, appears white. That's because it has minute fluid inclusions. These can be either gas or liquid or both that are trapped as the crystal is forming. Here are some images of fluid inclusions. These have a gas bubble, a liquid phase, and there's also a little solid phase in here. If there are other minerals entrapped in the quartz, then the color of those minerals can impart color to the overall crystal. So here, for example, are chlorite inclusions in quartz. This can also happen in calcite, and this causes the quartz crystals to appear green. Rutile is an orangey-brown crystal, so minute inclusions of rutile in quartz can give it a golden color. Other examples, carnelian is quartz that has inclusions of iron hydroxides, and prase, which is another green quartz, can have chloride in it, but some also has inclusions of actinolite. Iridescence is an interaction between Iridescence is a color that's caused by differential refraction of light waves through thin layers. Now, this can happen in lots of different materials, soap bubbles or insects or bird wings or oil slicks, but it can also occur with minerals. The color of the mineral is not actually the color of the iridescence. This is just a light effect associated with the refraction of light through thin layers. For example, the fresh surface of bornite is brown to coppery red color, but it tarnishes to form this iridescent purple surface. Some other copper sulfides can show the same kind of behavior. Opals also refract light to create these different colors. In this case, remember that the internal structure of opal is made of these little leptospheres. These have a particular radius that packs together to form these layers. The layers have specific thicknesses that allow the refraction of light to create these colors. Chatoyancy isn't necessarily a color, but it's an iridescence that's related to the interaction of light with minute fibers. So, for example, gypsum and tiger's eye quartz have fibers in them. Here is an example of gypsum. In tiger's eye, fibrous chrysotolite, which is an amphibole, has been replaced by quartz. It's been pseudomorphed by quartz to create this fibrous texture and this kind of interaction with light. Asterism is caused by the regular distribution of inclusions. So here, for example, is a garnet that has minute inclusions that are distributed in a way that light appears to form a six-pointed cross within it. Sometimes you'll see six-pointed crosses like here in Idaho star garnet, sapphire, and quartz. Other times you'll see a four-pointed star like here in feldspar and diopside. Labradorescence is also light refraction. In this case, labradorite has an intermediate composition. And if you remember back to our discussion of feldspars, feldspars often have solvi to them, meaning that two compositionally distinct feldspars will separate from a single compositionally intermediate feldspar. In this case, that separation of feldspars has a sufficiently small spacing to refract the light, and that's what gives rise to these different colors, usually in the green to blue range. Luminescence is when a mineral appears colored for reasons other than reflection or absorption. In this case, the mineral seems to glow or actually emit light. Often it's a reaction to ultraviolet light, although it can also be induced by X-rays or electrons. And here I'm going to talk about fluorescence and phosphorescence. Often when we look at minerals with ultraviolet light, they exhibit interesting colors. Here these electrons absorb the high energy of ultraviolet light and jump into higher orbits. As they drop down to their original orbits, they give off light in the visible spectrum. So here, for example, is calcite that's being illuminated with UV light. Here are willemite and calcite. And here you can see these colors are quite vivid and distinctive. Phosphorescence, again, the electrons are excited by UV light, But when you turn the UV light off, they continue to emit light. Then this is simply because the electrons are giving off light, but they're doing it slowly. So they drop back to their original orbits, but not immediately, and as a consequence, they continue to emit light for some period of time. Okay, so that concludes my lecture. I've talked about all of these different sources of color. I do want to direct folks to this website at the California Institute of Technology, which shows many beautiful images of minerals in the context of the causes of their color. Thanks.